and provided not any guarantees just because it had one, as long as that vulnerability wasn't found and exploited. So I motivated this so much because this is the most technical slide of the talk, so bear with me, and if not, no worries, it will get high level afterwards. So here is how we actually define security in this setting. Still a bit by example and figures, but somehow an instance of our definition. So say we have this program formed of 3 compartments, C0, C1, C2, which are all compiled. So this down arrow is my notation for compilation. And then are linked together. This hat are their interfaces. OK, not too important. And then I'm running them at the target level, say machine code level even. And then I obtain this trace prefix M, right? This is about the I/O behavior of the whole program. Like how does the program interact with the outside world? This might be things like library calls, system calls, things like this. And now this was a target level execution, and I would like to explain this target level execution. So if my compiler was secure, right? If the compiler I used to compile these compartments and the linker and whatever, if the whole chain and the machine, if all of that was secure, I would like to be able to explain this execution as a sequence of compartment compromises that explains this trace prefix in the source language. And here is how it could look at. Like, for instance, there could be some prefix of this execution trace M1 that ends up in undefined behavior in some compartment C1. So I run my program, say, in a source level interpreter, right, in a source level semantics. And it runs for a while, receiving the same inputs, producing the same outputs, right? This is what this M is about, until, I had undefined behavior, and now the source level semantics doesn't tell me anymore what's going on. And this, in fact, you would get, like this step, you would get just by the compiler correctness theorem of ComCert. So the compiler theorem, correctness theorem of ComCert if you would use like a verified compiler like ComCert, would tell you that, well, up to the first undefined behavior, the program has to produce the same trace as in the target. And this already captures a bit of this temporal aspect that the program still receives protection until compromised, but it doesn't capture the spatial aspects of just compiler correctness wouldn't capture the spatial aspect because, well, then all bets would be off. You wouldn't be able to explain the rest of the trace. So now what's new in the definition is that we have a way to explain the rest of the trace, right? In particular, we will take this compromised compartment C1, throw it away, and replace it with arbitrary source code A1 that now, well, can do arbitrary things, right, because it got compromised. It can try to compromise other compartments. And, well, let's say it succeeds, but it succeeds after running for a longer prefix of the trace M, like M1, M2. So in a way, I'm providing an explanation of a larger piece of the trace until another undefined behavior happened. It cannot be in A1 anymore, but it can be in the other compartments. For instance, A1 managed to compromise C2, right? And if this happens, well, we replay the same game again. We replace C2 with some arbitrary A2 until we are able to produce the same trace. So in this example, it happened after just 2 steps, but you can also imagine that the only explanation you can provide is that the attacker took over your whole program, right? It can also be an explanation. But the nice thing about it is it's given entirely in terms of the source level semantics. And this sequence of compromises, right? And the compromises are really done by an attacker that gives you bad inputs, either from the outside, right, via this trace M, or, well, via the high-level interaction between the compartments, like calls and returns and passing arguments and passing really long strings that overflow buffers or stuff like that, right? It's a high-level explanation that's not about, well, low-level attacks, compartment writing some other compartment's memory, right? It's not about low-level attacks. It's just about, well, attacks that can happen in the source, pretty much. However, with these situations in which you replace compartments with arbitrary code, right, when they get compromised. So this is how we define this. For lack of time, I won't get into much more detail, but one thing we proved in a paper a while back is that this can be reduced, so this is implied by a variant of robust safety preservation. So this idea of taking something and replacing with something else in the source, something that was, well, compiled over here and replacing it here with something in the source, this had exactly the same flavor, right, as robust safety preservation. Also, the fact that we are looking at finite prefixes of traces is about safety, so you can get an idea why. And we by applying repeatedly robust safety or variant of robust safety preservation, we obtain this iterative kind of construction. Okay? So in the remaining 5 minutes, I'll tell you about enforcement and proofs, but briefly. I knew I won't have much time for this. In particular, we've implemented this as an extension of ComCert. So the source language is a large subset of C, the one supported by ComCert, extended with this compartment, so this is like a module system, a very simple one. And then we have this C-comp compiler that targets RISC-V assembly of ComCert, but extended with compartment and with a magically secure semantics for this compartment. So this is just an abstract machine, right? That's trying to still be enforcement, how do you say, like not be specific to any kind of enforcement, because then we do enforcement in various different ways. One is software fault isolation, and then we are targeting just a vanilla machine without any special security features. Or we've been looking also at hardware accelerated enforcement quite a bit at this tagged architecture called micropolicies. But more, and this we've done in simpler settings, not for ComCert. For ComCert, we really built a Cherry RISC-V backend. And I'll tell you more probably in 2 slides about it. But the reason we were very interested in Cherry is, well, it's an academic project, but ARM had quite a bit of interest in it and had this experiment of actually producing an ARM processor with these capabilities in. So say if things were to continue in this direction and industry is convinced, this might be coming to your phone at some point. So it's not a completely crazy idea that this could be deployed in practice. And the nice thing about this hardware accelerated enforcement, well, it's usually faster than what you can do in software. And also you can do certain things like pass capabilities around between compartments that otherwise you wouldn't be able to do with software. Okay, so for ComCert extended with compartments, we added this mutually distrustful compartments with interfaces and interacted via procedure calls to all of the languages of ComCert. And we kept all the 19 verified compiler passes. We extended them to compartments, but they're all there, including all the optimizations. There's really only a footnote. Function inlining and tail call optimizations, we had to disable those cross compartments, but just because that changes the interfaces of compartments. So, but otherwise, well, other than this one little thing, you have all the optimizations of ComCert. And then we extended the compiler correctness proof in just 19,000 lines of code, which might seems like a lot, but compared with the size of ComCert, that's just a 13.6% change. And the nice thing is that I'm getting security in 2 slides. We are able to reuse that for the security proof, and that's really a big win. Now, the capabilities backend to this Cherry capability machine, I mean, capabilities are these pointers with a base and a bound, which you cannot access out of bounds. And we use them not to give us something like memory safety. You can also get that with Cherry, but really to only isolate compartments. So coarser-grained, like for instance, no, some other compartment will not get any pointer to any of the memory of another compartment, right? That's how we use these capabilities here. We are implementing this secure calling convention by INA, which uses some fancy kinds of capabilities or skip. And then because we are in this, as opposed to INA setting where it was really about a trusted versus an untrusted piece of code, here we have these mutually distrustful compartments. We also need to add some wrappers on calls and returns that do things like clean registers and make sure that these capabilities are not shared arbitrarily between compartments. So now, in terms of proof, how does one prove that a secure compilation chain at this scale achieves secure compilation? Maybe I should mention, in case it wasn't clear by now, that this kind of proofs are very difficult and tedious. For things like proof abstractions, conjectures have survived for decades. Like at POPL 6 years ago or 7 years ago, there was a paper showing that some conjectures made 20 years earlier about some transformation being fully abstract. Well, it wasn't true, and the POPL paper was just about, showing that it's not. And also proofs can get big, like even for total compilers, 250 pages. I've seen this kind of proofs. So we are working on more scalable proof techniques, trying to reduce proof size, but also working with machine check proofs in the Coq proof assistant. I mean, at the scale of ComCert, there's really no other way of. There's no paper proofs at that scale. And as a stopgap, we are also using property-based testing to find wrong conjectures early, and also to deal with parts that we don't know yet how to verify. So here is how this looks for our compilation chain. For the ComCert part, we have full machine check proofs in Coq. We have the scalable proof technique. We first apply to simple languages, made sure first that it works in the small before trying it at ComCert scale. Then we scale it up. The nice thing is that it reuses this ComCert correctness proof, which is really super large, 130,000 lines of code. And our security plus the extensions of just the correctness proof, so everything we added, is only about 1/3 of the correctness proof of ComCert, the original correctness proof of ComCert. And this is really a milestone in terms of realism. In this space of full abstraction-like proof, people were really only doing things for very simple languages, while here we are able to do it for an optimizing C compiler with 19 passes. And in the past, we've used systematic testing to verify some of our backends, to systematically test, to validate our backends. But it would be very nice to also verify these backends, because that's where the interesting thing is happening in terms of enforcement. But yeah, it's a verification challenge, and I don't have time to go into the detail why it is, but I'll stop here and take questions.
Thank you, Cătălin. One question, and then we should go to lunch, I think. Yes.
So I'm curious, like when you say sort of verification for this kind of lower sort of like target languages.
Backends, yes.
Yeah, backend. So like, what would that even entail? Because obviously, like, you can't feasibly verify like an actual physical processor or whatever. So like,
no, but
what type of specification are we talking about verifying here?
Yeah, I mean, one usually stops at the level of the instruction set architecture, right? So the the processors usually give you a relatively clean interface that tells you pretty much an operational semantics for all the instructions, and that's good enough as a operational semantics against which to verify things.
Right. So in this case, for example, like you would be showing that the cherry capabilities are enough to encode the behavior that you get from compartments.
Yes.
Okay.
Exactly.